Okay. So in the last class, we looked at the definition of Nash equilibrium and we saw how to find a Nash equilibrium in the matrix format. We saw basically how to get to the Nash equilibrium, right? So now and then we looked at Battle of the Sexes game, right? So in Battle of the Sexes, we saw that there are two Nash equilibria. One is ballet ballet. Okay, so ballet ballet is a Nash equilibrium and boxing boxing is a Nash equilibrium. Okay, can anybody tell me what was the definition of Nash equilibrium which I told you to remember? What is Nash
Then
equilibrium?
no player has an incentive to deviate.
Very good. Okay, so no player has an incentive to deviate. Okay, so this is the most important thing that you need to remember about Nash equilibrium. That Nash equilibrium implies that no player has an incentive to deviate. So I'm saying that this is a Nash equilibrium outcome. Now from here, if the wife deviates, these are wife strategies. So wife is a role player. So wife goes from ballet to boxing. So her payoff goes from 2 to 0. On the other hand, if the husband deviates, then his payoff goes from 1 to 0. So nobody has an incentive to deviate from this strategy profile. And similar analysis gives me that from here, if the wife deviates, her payoff goes from 1 to 0. And if the husband deviates, his payoff goes from 2 to 0. So nobody has an incentive to deviate from either of these strategy profiles. Okay. But this is pure strategy Nash equilibrium. Then I gave you this rock, paper, scissors game. And we saw that in this game, there is no pure strategy Nash equilibrium. Okay, so PSNE is pure strategy Nash equilibrium. So obviously, when we are talking about pure strategy Nash equilibrium as one type of Nash equilibrium, then it begs the question, is there any other type of Nash equilibrium which exists? And the other type of Nash equilibrium which exists is mixed strategy Nash equilibrium. Now, mixed strategies are not in syllabus. Strictly speaking, it's not in syllabus. But I had made one point earlier, which was basically that Nash equilibrium is the intersection of best responses. So one definition which I want you to remember is Nash equilibrium is no player has an incentive to deviate. That will do your job. But there's another definition of Nash equilibrium, which is that it is intersection of best response functions. So I want you to be able to appreciate this definition, and that's why I'm going to do a little bit of mixed strategies. Also, it builds some understanding of how basically optimizing expected utility. So we can look at optimizing expected utilities. Okay. So first of all, what are mixed strategies? So a mixed strategy is basically you do not pick ballet or boxing with certainty. You do some sort of a probability distribution over ballet and boxing. So for example, both this husband and this wife, they get free after office. And what they do is that both of them, they take a coin and they flip. The husband takes a coin and he flips the coin. If he gets a head, he goes to the ballet performance. If he gets a tail, he goes to the boxing performance. Similarly, the wife also flips a coin. If she gets head, she goes to the ballet performance. If she gets a tail, she goes to the boxing performance. So now what's happening is that they are not picking any particular strategy with certainty. What they are doing is that they are randomizing between the strategies with some probability. So essentially, they are both playing these probabilities with both playing these strategies with probability half each. They could alternatively be choosing some other probability profiles. Okay, maybe not head or tail. They could just be choosing probability P1 minus P and Q1 minus Q. So such a profile is called a mixed strategy Nash equilibrium if no player has an incentive to change these probabilities. Okay. So if husband is playing P1 minus P and wife is playing Q1 minus PQ, neither of them have an incentive to change these values. When that point is reached, we say that you have reached the mixed strategy Nash equilibrium, provided neither of these values is zero. All these values need to be strictly positive, because if any of these things becomes zero, then it essentially becomes a pure strategy equilibrium. Suppose Q becomes zero, then wife is basically playing boxing with probability one. So this becomes a pure strategy for wife. So if I want it to remain a mixed strategy equilibrium, then P1 minus P, Q1 minus Q, they should all be strictly positive. Only then it qualifies as a mixed strategy Nash equilibrium. Okay. So how do I find this mixed strategy Nash equilibrium? For that, first I want to find the payoffs. So remember, the payoff matrix was if both of them play ballet, this was the husband, ballet, boxing, then ballet, boxing for the wife. The payoffs were 2-1, 0-0, 0-0, and 1-2. Okay, so these are the payoffs. Now suppose the randomization is happening with this profile. This is the profile of randomization which is happening. So with this profile of randomization, what will be the expected utility of wife? Okay, so for that I have to find the probability of each of these things happening. So what is the probability that both of them end up at the ballet performance? Both of them are taking a coin and flipping it. If head comes up, the husband goes to ballet. If head comes up, wife goes to ballet. So what is the probability that both of them end up at the ballet performance? What is the probability of this outcome?
1/4.
1/4. Very good. So this will happen only if both of them get head. Okay, what is the probability of this outcome, that both of them end up at the boxing performance?
This is also 1/4.
Very good. In fact, all of these are going to be 1/4. Okay, so expected utility of wife is the wife gets a payoff of 2 with probability 1/4, plus she gets a payoff of 1 with probability 1/4. So that is 3/4. Okay. Now, Madhur, what is the expected utility of husband? Are you with us, Madhur?
Yes, sir.
What
Am
is
I
the
audible?
expected utility of husband?
Sir, 1/4.
What, 1/4?
Sir, 1/4 into sir 1/4 into 0. Sorry, sir, I'm lost somewhere.
Okay, can anybody else pitch in?
Yes, sir.
So
1/4 into 1 plus 2 into 1/4.
Very good. Okay, so 1/4 into 1 plus 2 into 1/4. So that's going to be 3/4. All right, so both these people. So this is how we calculate expected utilities. All right. Now let's say I don't live in these probabilities. Okay, now let's do the analysis for random probabilities. P, Q, and 1/P, 1/P. Okay. So now the wife is playing ballet with probability P, this with probability 1 minus P. The husband is playing ballet with probability Q, this with 1 minus Q. So these numbers will change, right? So now the expected utility of wife becomes, okay, so who do I have other than, yeah, Kritika. What is the probability now? So if these are the probabilities of different strategies being played, so Kritika, what is the probability of the game ending in this cell?
So P into Q,
P into Q. And this cell?
1 minus P into 1 minus Q.
Very good. So the remaining are immaterial because the numbers are zero. So can you tell me the expected utility of wife, Kritika?
So that will be 2 into PQ plus 1 into 1 minus P into 1 minus Q.
Very good. Okay, so this is the expected utility of wife. So similarly, I can write expected utility of husband. I'll do that later on. Okay. For now, let's focus on what's happening to the wife. So now this wife has an expected utility of 2pq plus 1 minus p into 1 minus q. Now, what is the number that the wife can control? She can only control
सर
p. Yeah.
सर सर PQ वाला वो part समझ नहीं आया. So 2
Because
into PQ plus 1 into 1 minus P
what
into
is, do
1
you
minus.
understand this pq?
No, sir. So
The
P and
husband is playing ballet with probability q. The wife is
yes.
playing ballet with probability p. So the probability that these are independent events. So the probability that both of them end up at the ballet performance is going to be P into Q. This
Okay.
is wife showing up for ballet and this is husband showing up for ballet. So this is P into Q.
Okay.
Have you done probabilities?
Yes, sir.
So this is just simple probability of independent events. Earlier probably P and Q were half each. So that's how we reached that 1 by 2 into 1 by 2. So that was 1 by 4. Now I am giving the probabilities as P and Q. So this is probability P into Q. So just multiply these numbers. Okay.
Sir, also,
Okay, sir.
I had a doubt. I was not there in the previous lecture. So, how do we decide that the utility is 2 and 1?
That is given to us in the question.
Okay, it's given.
Uh, so this is my expected utility of the wife. Now the only variable which the wife controls is P. So I can write it as expected utility of wife as a function of P. So now what she wants to do is she wants to maximize expected utility as a function of P. So what she wants to do is she wants to optimize this function with respect to P. So she takes Q as a constant. Why does she take Q as a constant? Because she cannot control Q. The husband is controlling Q, right? So for her, she is, as far as she is concerned, Q is a state of nature for her. She cannot control it directly. Okay, indirectly maybe she can threaten his husband. Q, ye khelo. That's all not part of the story. The part of the story here is that these are independent actors and they can only control their strategies, not the strategy of the other person. So P is something that this wife can control. So what she's going to do is del expected utility of y by del P. I'm going to look at this thing. So this becomes 2Q minus, sorry, 2Q plus differentiation of 1 minus P is minus 1 into 1 minus Q. So that is 3Q minus 1. So this is the del expected utility of y by del. Okay. All right. Yuvakshi, what are the values which Q can take? Hello, Yuvakshi.
Yes, sir.
Yeah, what are the values which Q can take? Q is a probability with which husband plays ballet. So what are the values which Q can take? What are
0
the
to
set
1.
of values? 0 to 1, very good. Okay. So the slope of the expected utility of wife is 3Q minus 1, where Q takes values between 0 and 1. Right? So this slope del expected utility y by del p, this is going to be positive if Q is greater than 1 by 3 and negative if Q is less than 1 by 3 and 0 if Q is equal to 1 by 3. So let's focus on a situation where Q is 1 by 3. But remember, Q is the probability of husband picking ballet. All right. So Q greater than 1 by 3 means the husband is choosing ballet with a probability greater than 1 by 3. So when Q is greater than 1 by 3, this slope is positive. Okay. Now P also belongs to the same range, by the way. P also belongs in 0 to 1. Now focus on this function expected utility. Expected utility is a function for which slope is positive and the domain is 0 to 1. So what would be the optima of this function? So again, expected utility is any function on the domain 0 to 1 with a positive slope. So a function with a positive slope, where will its optima be? Where will its maxima be? Sorry, the maxima.
At 0, right?
It's an increasing function. Think of any increasing function. Where will the
So 1.
maxima be?
So
1.
1.
Exactly. The max point on its domain, 1. All right. So if Q is greater than 1 by 3, then the optima for the wife is P equals to 1. Now, if P is less than 1 by 3, then the slope is negative. So it's a decreasing function. So where will the optima be?
0, right?
0.
0. Okay. And if Q equals to 1 by 3, then the slope is 0. So it's a constant function. So for a constant function, what is the optima? If this is the domain, what is going to be the optima? What is going to be the maxima? I should use the word maxima instead.
Any point between 0 and 1.
Very good. Absolutely correct. So this was a technical question. Any point P belonging to 0 to 1. The entire set is maxima. So she can take any P. It does not matter. It will not matter. So what's happening here is, remember that Q is the probability of the husband picking ballet. Now, remember that the wife gets a greater payoff with ballet as compared to boxing. So obviously, if the husband is going ballet, if the husband is much more likely to go to ballet, you should always go to ballet. P equals to 1 means what? You always go to ballet. You take the chance. Okay, you take the chance. Okay, I don't know what the husband is going to pick. But if he is more likely to come to the ballet performance, I should just stick to the ballet performance and not play the uncertainty game at all. On the other hand, below some threshold value, that is Q less than 1 by 3, the husband is picking boxing much more often. Right? So if Q is less than 1 by 3, it means 1 minus Q, which is the probability of going to the boxing performance is pretty high. So the husband always goes to the boxing performance. So think of it this way. Suppose Q is 0. So the husband always goes for the boxing performance. So what should the wife do? She should simply go to the boxing performance as well. Because any time that she goes to the ballet performance, she's going to incur a payoff of 0. Remember these numbers. Okay, if the husband is always picking boxing and you pick ballet, you are going to end up at 0. Right? So it's true for the husband always going for boxing, or any probability in which husband picks boxing way more often than going for the ballet performance. So the threshold at which this change happens is 1 by 3. That is something we derive mathematically. But analytically, the thing is very simple. If the husband always goes for ballet, you should go for ballet. If the husband always goes for boxing, you go for boxing. Okay, so that is something pretty analytical. So some place closer to always ballet. Let's say the husband picks ballet 99% of the times, then it is going to yield a similar result. You should keep going to ballet. And if the husband goes for boxing 99% of the time, you should keep going for boxing. So at some point, the threshold is breached, and that threshold is breached at 1 by 3, which you have to find mathematically, which we just did. All right. So this was the entire story for the wife. So if I want to plot the best response curve of the wife, then it would look like this. So suppose this is P, this is Q, which is the probability of husband. This is P, the probability of wife. So for Q equals to 1 by 3 is the threshold. So till Q equals to 1 by 3, till Q is less than 1 by 3, you play P equals to 0. So P is 0 here. Then it moves along this line, the dashed line. And when Q becomes greater than 1 by 3, you pick P equals to 1. So okay, so this is the best response curve of the wife. Now I want to do a similar analysis for the husband. So first, tell me the expected utility function of the husband. Using this table and probabilities, what is going to be the expected utility function of the husband?
PQ into 2, PQ plus 2 into 1 minus P into 1 minus.
Very good. So expected utility of husband is 1 times PQ. So that is PQ plus 2, because with PQ probability, he gets a payoff of 1. And with 1 minus P, 1 minus Q, he gets a payoff of 2. So plus twice into 1 minus P into 1 minus Q. Now, what is the variable which the husband controls?
Q.
Q, right? So I'm going to differentiate it with respect to Q. So what do I get when I differentiate this with respect to Q? This P minus twice into 1 minus P. So that is 3P minus 2. Right? So this function is basically positive if P is greater than 2 by 3. Is negative if P is less than 2 by 3, and is 0 if P equal to 2 by. So again, this is my expected utility function. described on the variable q, and remember that q takes values in 0 to 1. So if this function is, if p value is greater than 2 by 3, this function is increasing. So what should be the ideal q value?
So 1.
1. I'm not saying the maximum expected utility kya hogi hai. What I'm saying is, at what q will expected utility get maximized? I'm not asking the maximum value for expected utility. I am finding the input value q at which the expected utility of the wife gets maximized. All right. Here it should be q equals to 0, and here it could be q belonging to 0 to 1, anything in 0 to 1. Okay. So now the critical p value is 2 by 3. So let us highlight that 2 by 3. Now till p equals to 2 by 3, q is 0. So q is 0 till p equals to 2 by 3. At p equals to 2 by 3, q can be anything along this dashed line. And that dashed line is okay. Okay. And at q, okay. And above q 2 by 3. So q greater than 2 by 3 is basically this region. Right. So here the optimum will be happening at q equals to 1. So it should be along this. So this entire curve, this, this, this entire 3 line segments together, this is the best response of husband. Now I'll come back to the intersection bit, but first I want to discuss this point about what happens when QP is 2 by 3. So why don't you substitute P equals to 2 by 3 here and tell me what will be the expected utility of the husband when P is equals to 2 by 3. What will be this value?
So 2 by 3.
So it's going to be 2 by 3 into Q plus twice into 1 minus P is 1 by 3 into 1 minus Q. So that is 2 by 3Q plus 2 by 3 minus 2 by 3Q, which is 2 by 3. So what this means is that when the wife is randomizing between ballet and boxing with probability 2 by 3 and 1 by 3, the husband's strategy is immaterial. It does not matter what the husband does, because then the expected utility of husband is independent of, and that's why we see that this expected utility function is constant at 2 by 3. Basically the Q term cancels out. This is why I'm seeing all these points as the optimum. Now coming back, the intersection points. So there are 3 intersection points of the red and black curve. This, and this. So this point is 0, 0, P0, Q0, which basically means that both of them play ballet with 0 probability. So this is just the pure strategy boxing. And this point is 1, 1, which is just the pure strategy ballet. But this is a new equilibrium, new new Nash equilibrium which I obtain, in which I see P equals to 2 by 3 and Q equals to 1 by 3. So this is a mixed strategy Nash equilibrium. So how do I set up this mixed strategy Nash equilibrium? So the husband, he plays ballet with probability 1 by 3 and boxing with probability 2 by 3. And the wife, she plays ballet with probability 2 by 3 and boxing with probability 1 by 3. So in that case, what I see is that 0, 0, 0, 0, 1, 2. In this case, you will have a Nash equilibrium. Now, why do I have a Nash equilibrium? The story is here. Because as you can see here, what's happening is that if the wife plays P2 by 3, then the husband doesn't care what he plays. He has no incentive to deviate because his deviation is changing Q. But whatever Q he picks up, the husband always gets a payoff of 2 by 3. So he has no incentive to deviate. And similarly, as long as the husband is playing this probability 1 by 3, the wife has no incentive to deviate between different values of P. So as long as P is 2 by 3, the husband has no incentive to deviate Q, and as long as Q is 1 by 3, the wife has no incentive to deviate 2 by 3. So that's why this becomes a Nash equilibrium. Okay. That said, this is not in syllabus, but I still like to discuss it because it clears up some more conceptions about uh, Nash equilibrium and what it means for the Nash equilibrium to be intersection of best responses. So that's why I like this topic. It's not in syllabus, never asked before. Although they will give this word PSNE. DSE asks questions. When it asks, it gives you a game and it asks find all PSNE. So pure strategy Nash equilibria it will ask you. So you should know that what is pure strategy. And to explain what is pure strategy, I need to explain what is mixed strategy. Okay, because it's like trying to explain day, the concept of day to somebody who does not understand the concept of a night. You have to sometimes give the concept of what else is there apart from this to make somebody understand what is the importance of something. So to understand the importance of pure strategies, one has to look at mixed strategies. Okay, by the way, a deviation, this entire things, these are all the work of John Nash. So one very interesting statement which John Nash gave, which he proved, was that in mixed strategy Nash equilibrium, every game has an odd number of equilibria. If you allow for mixed strategy Nash equilibria, every game will have an odd number of equilibria. Mixed plus pure, by the way. When he says mixed strategy, John Nash includes pure strategies into mixed strategies. Okay, so for him, pure strategies are just mixed strategies with some probability 0. So that was mixed strategies for John Nash. So the importance of that is that you see this game, you have 3 Nash equilibria. That's odd. Okay. Then we had our prisoner's dilemma game that had 1 Nash equilibrium. So if you find any game which has 2 pure strategy Nash equilibrium, then it will have at least 1 mixed strategy Nash equilibrium, because the total number of Nash equilibria has to be odd. Now, why am I saying this? I'm not going to give any proofs or whatever. The reason I'm giving this is that sometimes in odd exam, in objective exams, this might be useful. So suppose if you remember this, and there's one of the options which you can pick as correct using just this statement, then maybe it will ease up your job. Okay, so although mixed strategies are not in the syllabus of DSE or ISI, I cannot say the same about other exams. So maybe they ask you in JAM or somewhere else. So I cannot be sure because these are recent exams. So we don't know how deep they want to go in any topic. All right, so that's about mixed strategy Nash equilibrium. Okay, so this is how it looks, the intersection of mixed best responses. Okay, now let's do this example. Find all mixed and pure strategy Nash equilibrium for the following. So obviously this example is a 3x3 matrix. So that is going to be a little more difficult because then we have to take probabilities P1, P2, 1 minus P1 minus P2, Q1, Q2, 1 minus Q1 minus Q. So that's going to be very difficult. So in questions like these, sometimes you can eliminate some of the rows or columns. So to see that, look at the numbers. So look at these numbers, 241 and 130. Okay. So 2 is greater than 1, 4 is greater than 3, 1 is greater than 0. So no matter what strategy the row player plays, A2, B2 or C2, playing A1 always gives a better payoff than playing B1. So we say that the strategy B1 is strictly dominated by strategy A1, or A1 strictly dominates B1. The field is the same, right? Because no matter what the row player plays, playing A1 always gives a better payoff than B1. So you can eliminate this entire column. Okay. Now, when I eliminate this entire column, then look at these two rows. 2 is greater than 1 and 3 is greater than 2. So what I can say is B2 strictly dominates C2 because no matter what this guy plays, A1 or C1, B2 always gives better payoff than C2. So what you can do now is you can eliminate the last row because the last row is also strictly dominated. So this becomes a 2x2 matrix. Now I'm going to further see if I can remove anything. So let us look at the row player. So for the row player, I'm going to look at the numbers. So 2 is greater than 0, but 4 is greater than 3. So the row player does not have any dominated strategies. Let us look at the column player now. So for the column player, when this guy plays A2, then 3 is better. But when this guy plays B2, then 4 is better. So there is no dominated strategy now. So I cannot eliminate anything after this point. So I can eliminate these two rows and columns. After that, what I'm left with is this smaller game, A1, C1, A2, B2, 0, 2, 4, 3, 2, 4, and 3, 2. Find the pure strategy Nash equilibrium.
So 4, 3 and 2, 4.
Okay, so Rityan is saying that both these cells represent pure strategy Nash equilibrium. I'm waiting for everybody else to do this.
So 4, 3.
Just one?
Yes, sir.
Okay.
So 4, 3.
Okay, so two of you are saying just 4, 3. Others, what are your opinions?
4, 3, 2, 4.
Okay, both of them. Who was this? Mother. Okay. So I have 2 votes for this, 2 votes for this. So yeah, so let's analyze this using my star mark technique. Okay. So I'm going to first look at the row player. So fix the strategy of column player as A1. So then the best response of this guy is 2. And when you fix it as C1, then the best response is 4. Now let's look at the column player. So when I fix the strategy of low player as A2, then playing A1 gives him 2, playing C1 gives him 3. So 3 is larger. So this is 1. And when I fix it as B2, then playing A1 gives 4, playing C1 gives 2. So 4 is larger. So this. So both these are Nash equilibrium. Now, from the John Nash's rule, which I told you, the theorem, there has to be at least one mixed strategy Nash equilibrium. Okay. Now the thing is, since it's not in my syllabus, I don't need to do it. But if you want to find mixed strategies using the maths I just told you, you can frankly eliminate C2 and B2 from the discussion completely. Just use these as the strategies to find mixed strategies. The probabilities, and the probability of playing C2 and B2 in any mixed strategy would also be 0. Okay, they are dominated strategies, they will never be played. Okay, now coming to B part, can you tell me any dominated strategies? Dominated strategies or dominant strategies, anything? You guys are looking at this game, right?
So 4, 4.
You're saying 4, 4 is the Nash equilibrium? I'm first asking about dominated or dominant strategies, Rityan. Maybe you're right. I don't want to jump there right now. Because using the star mark technique, finding Nash equilibrium is pretty easy. So I'm guessing all of you could do it in exam, even if you guys have not done it right now. But I'm hoping by the time of the exam, you guys will be pretty adept at it. But here I'm just asking for you to look out for dominated strategies or dominant strategies. We talked about dominant strategies in the last class in the prisoner's dilemma.
So does C2 dominate B2?
Yeah, C2 dominates B2. Very good. So we see 3 is greater than 0. Sorry, no. C2 dominating B2. No,
So C1 dominates
no.
B1.
Yeah, C1 dominates B1. That is correct. So when you're talking about C2 dominating B2, you have to look at these numbers because you're talking about the row player, right? So when you're looking at these numbers, then B2 is greater in the first number itself. So if you fix column player strategy as A1, then it's better to play B2 over C2. But when you fix it as B1 here, then it's better to play C2. So neither of these strategies dominate the other. Okay, but Kanishka's answer is correct. C1 is dominating B1. In fact, C1 is a dominant strategy. A dominant strategy is one which dominates every other strategy.
So, if C1 dominates C1, like if the player is playing A2, then it's better to play C1. And if the
Yeah.
player is playing B2, then it's better to play B1.
No, it's not.
So
Wait.
it's 0, 1, and 2, 1.
Oh, no. Sorry. Yeah. Mm. Yeah. You're right. Sorry, I was seeing these numbers. Yeah. You're right. Yeah. So there is no dominance of C1. Sorry, I take back. I made the mistake of seeing these numbers. It happens time and again. Uh, so I should be looking at these numbers, the second numbers when I'm looking at a column player. So C1 is a strategy of the column player. So I should be looking at these numbers when I'm looking for dominant or dominated strategies. And when I'm looking at the row player, I should be looking at these numbers: 114, 203, and 023. So as you can see, there is no dominant or dominated strategy here, right? So here we use a trick which comes in mixed strategies, but I don't want to go into that trick and everything because mixed strategy is anyway not in the syllabus. So yeah, so in this one you have no dominant or dominated strategies. I should ideally change this game and give you a different one. I used to teach this trick, but I don't see the point because I'm teaching anyway more than what is required in mixed strategies. Then we get completely lost in these things itself. Let me change this game a little bit so that we can understand a little bit more about mixed strategies. dominated strategies. So let's say these numbers are 3, 3, 4. Okay, let's say these numbers are 3, 3, and 4. Then we see that C2 is a dominant strategy. What do you mean by a dominant strategy? A dominant strategy is something which strictly dominates each and every other strategy. Okay, so as you can see, 3 is greater than 0 and 2. This 3 is greater than 2 and 0, and this 4 is greater than 3 and 3. So C2 is a strictly dominant strategy. So what happens in this game is that the row player always picks C2. He always picks C2. So you can completely eliminate the first two rows. So only this is going to be played. Now when only this is going to be played, the column player strategies are A1, B1 and C1, of which C1 is the highest. So this is going to be your flash. Okay. So this is dominated and dominant strategy. So sometimes if they give you bigger games, maybe it comes in handy. Ideally, they have not given any such game till now. They have not given any 3x3 game at all. They at max they have gone to 3x2 games. But maybe in future they go there, and so when you see a situation like that, maybe they ask you which strategy is dominated or which is dominant, because dominated strategies and dominant strategies are in the syllabus. Mixed strategies is not. Okay, so mixed strategies is not in the syllabus. All right, now let's do a continuum of actions. So in continuum of actions, we till now we had allowed for the strategies to be a discrete set, right? So it can only be either ballet or boxing, or it can only be to think or to remain silent. So the strategy set was a discrete set. Now we are going to allow for the strategy set to be a continuum. Continuum means it can be some interval of the format A to B, any type of bracket, or it could be entire real number line, or entire R plus, or entire R plus plus. So continuum of actions is interesting in economics, because in economics, when we study the firms, the actions of firms are either to pick the quantity they want to produce or to pick the price they want to sell. And you see, quantity is R plus, price is R plus plus. Right? So quantity can be any non-negative quantity, price can be any positive price. So the strategy sets of firms are actually continuous. Now, why are we looking at this? So remember that in consumer theory, we looked at how the consumer forms demand. In producer theory, we looked at how a firm generates the cost function. Okay, so this was demand function. This was cost function. Cost function gives you the marginal cost function. Now in game theory, I will see that in strategic situations, when two firms are going head to head against each other, how are they going to decide how much of quantity to produce or uh, how much of price to charge in the market? All right. So let's look at this example. So two herders who choose to graze their sheep on a patch of land and produce wool. The inverse demand function for wool in the market is 120 minus Q1 plus Q2, where Q1 is the number of sheep herded by herder 1 and Q2 is number of sheep herded by herder 2. Okay, so the demand function is P equals to 120 minus Q1 plus Q2. So P equals to 120 minus Q1 plus. We are going to assume no cost of production. So both these herders, they live in a village where there's large swaths of open land where you can take your sheep for grazing. Nobody asks you any question. You don't have to pay anything. So you can graze as many sheep as you want at no cost. So cost of production is zero. Okay. This is the the demand function or the inverse demand function. Okay. So this is the inverse demand function. Okay. So demand function is Q as a function of P, and the inverse demand is P as a function of Q. Right? Y as a function of X is a function, then X as a function of Y is the inverse function. So that's like this. It goes like this. So if this is my demand function, I write this as the total quantity Q. Then I can replace this to write Q equals to 120 minus P. So this becomes my demand function. Okay. So when you write P as a function of Q, it's inverse demand. When you write Q as a function of P, it's demand. Okay. So sometimes in exam, they will write this as demand function. Sometimes they'll be terribly correct and they'll write it as inverse demand function. So don't get all confused. Inverse demand. Okay, so some textbooks write this function as demand function because it's the same function. You just rearrange P and Q. That's all you get. Some textbooks will call it as inverse demand. So don't bat an eye about it. Kya ho gaya ye? Basically, this is the relationship between price and quantity. So how do I do that? So suppose I want to write a profit of firm 1. So profit is price into quantity minus cost of producing this quantity Q1. So price is given by this relationship 120 minus Q1 minus Q2 into Q1. This is my revenue. Minus cost is 0. So I'm just eliminating the entire cost. So this is profit of firm 1. Similarly, profit of firm 2 can be written as phi 2 is equals to P into Q2. Cost is absent. So 120 minus Q1 minus Q2 into. Now I want to find the best response of these firms. So best response function of firm 1. To find this, what I need to do is del pi 1 by del Q1. Because Q1 is the quantity which firm 1 controls. So it will take Q2 as constant here. Okay. So that's why the partial derivative, because I'm taking Q2 as constant. So del pi 1 by del Q1, what will that be equal to? So this is my.
So 120 minus 2Q1.
What about Q2?
minus Q2 bar.
minus Q2 bar. So I'll just write it as Q2 because this bar was just to tell you that this is a constant for firm 1. Firm 1 takes it as a constant. Okay, so 120 minus 2Q1 minus Q2. So this is equals to 0, which implies my Q1, which is the ideal quantity I should produce, should be equal to 120 minus Q2 by 2. So if I were to find out what quantity the other firm is producing, I can use this knowledge of Q2 to generate what should be the profit maximizing quantity I should be producing. So if I were to plot this best response curve on Q1, Q2, so this is my, let's say, Q1, and this is, let's say, Q2. So I want Q1 as a function of Q2. So when Q2 is 0, Q1 is 60. So Q2 0, Q1 is 60. And when Q1 is 0, Q2 should be 120. So this is the best response of firm 1. Now this is best response. Now I want to get best response of firm 2. So del pi 2 by del Q2 equals to 0, which implies what? What would be the relationship I get when I differentiate this and equate it to 0?
So 120 minus 2Q2 minus Q1 is equal to 0.
Which implies now that Q2 must be equal to 120 minus Q1 by 2. So now I want to plot this best response curve. This is best response of firm 2. So when Q1 is 0, Q2 should be 60. So that would be here. And when Q2 is 0, Q1 should be 120. So this is best response of firm. So this is my intersection point, which is going to be the intersection of these two system of equations. Solve these two system of equations to give me Q1 and Q2.
So 40, 40.
Okay, so Kanishka says Q1, Q2 should be equal to 40, 40. Waiting for other answers.
Yes, sir. Same.
Who gets a similar answer? Anybody else getting a different answer? Does somebody need more time?
Yes, sir. 40, 40.
All right. So is anybody still solving? Should I wait more?
Sir, 1 minute, sir.
Okay. So in the meantime, I want others to solve the second part of this, in which okay. So herder one is a branded customer, is a branded wool. So price for herder one is 140 minus capital Q, where capital Q is Q1 plus Q2, whereas price for herder two is still 120 minus capital. Everything else is same. So what will be the Nash equilibrium? Q1 star comma Q2 star. That is what is the equilibrium Q1 Q2. All right, so everything else remains the same. For your ease, let me show you the entire calculation for the previous bit. This can be shown easily. I hope you can see the entire calculations for the previous one. This is the second part. Example 2. Okay, so I'll just be back while you guys solve this one. Yeah. So do we have any answers? One 60 by 3 and 100 by 3. 100 by 3. So somebody saying 100 by 3, somebody saying 200 by 3. So I'll have to solve it. Hmm. So pi 1 would become, okay, firm 1 is charging a higher price. So pi 1 would become 140 minus Q1 minus Q2 into Q1. which implies del pi 1 by del q1 equals to 0 becomes 140 minus 2q1 minus q2 equals to 0, which implies q1 equals to 140 minus q2 by 2. And similarly, best response for form 2 would be 120 minus q1 by 2. And then you simultaneously solve this system of equations. So q2 becomes 60 minus q1 by 2. So q1 is just 140 minus q2 by 2. So q2 equals to 60 minus 140 minus q2 by 4. So I'm only finding q2 because there was some ambiguity in q2. So 4q2 must be equal to 240 minus 140 minus q2, which is basically 100 plus q2. So q2 must be equal to 100 by 3. So q2 is 100 by 3 and q1 was, what did you guys tell me? q1 160 by 3. So clearly now q1 has an advantage in that uh, it it can command a larger market share because it's a big brand. In this case, what will be P1 minus P2? This was my P1, this was my P2. So what will be P1 minus P2?
Twenty.
20, very good. Okay, you don't need Q for that. For whatever Q, P1 minus P2 will always be 20, which implies that P1 is greater than P2, Q1 is greater than Q2. So firm 1 definitely has a higher profit margin. So the profits of firm 1 are definitely going to be larger. Okay, so if you are a big brand, a renowned brand who can sell your products at a higher at a premium, then you are definitely going to get a larger. Profit. So this is what happens in this case. So in this case, what happens is that the best response curve of firm 1 shifts out. Initially, both responses were 120 minus q bar by 2. But now best response of firm 1 becomes 140 minus q2 by 2. Okay, so it will shift outwards. So the intersection shifts in this direction, which is downward for firm 2 and rightward for firm 1. So firm 1 increases its sales, whereas firm 2 loses its sales. Okay, so these are some takeaways from this variation, which maybe they ask you. So they give you first part as the general Cournot and the second part as this deviation. All right, next up we have sequential games. So in sequential games, what happens is that people don't play simultaneously. So there are two types of games, simultaneous and sequential. So in simultaneous, what happens is it's not that all players play their strategies exactly at same point. The English meaning for the word simultaneous is at the same point of time. It does not mean that you will play exactly at the same time as I do. It's just that when you make your strategy, I do not know what, sorry, when I make my strategy, I do not know what your strategy is. Basically, I'm making my strategy without having a look at your strategy. That is simultaneous. So in simultaneous games, people do not know what the other guy is doing. But in sequential games, we say that the information is public. So the first player moves, then the whatever the strategy of first player is, it is revealed to all the people. So in sequential games, basically what happens is that suppose you have a game of chess. So game of chess is sequential. I move, then you move, then I move, then you move, and so on. So that's a sequential game. In fact, most sports are sequential games. Okay, so in tennis, the server plays the ball first, then the returner sees what type of serve has been cast, and then he decides his strategy. So most games are sequential games. Simultaneous games happen in policy making, especially defense policy. So when I'm choosing some military strategy, I do not know what military strategy my counterparts are choosing. So that's in real life, that is something like a simultaneous. So till now we have only studied simultaneous games. We did not look at sequential games. So let's look at the battle of sexes in sequential format. So this is how battle of sexes looks in sequential format. So suppose the wife is the first to play and the husband is the second. So these black dots, they are called decision nodes. So at every point where some player is making a decision, it's called a decision node. So first the wife makes a decision to play ballet or boxing. Suppose the wife picks ballet. So you reach this decision node. Now the husband must pick between ballet and boxing. Okay. Similarly, if the wife moves boxing, then the husband reaches this decision node and then he must pick between ballet or boxing. Okay. So in this case, we say that the husband really has 4 strategies here. The strategies of husband are 4, not 1, or not 2, but 4. One is playing ballet after seeing ballet. Other is playing boxing after seeing boxing. One is playing, ballet after ballet, boxing after ballet, ballet after boxing, boxing after boxing. So these are the 4 strategies of the second player, that is the husband. So the strategy set, so the strategy set of husband contains strategies ballet, 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 boxing, 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 and boxing, ballet. Where the first number represents the strategy played on decision node 1, which is the decision node reached when wife plays ballet. And the second number, so the second strategy in each vector is the strategy played on decision node 2, which is reached when the wife plays boxing. Okay, so these are the 4 strategies of the husband. So if I were to write the matrix format of this game, so now my wife is continuing to be the role player with ballet and boxing, but the husband has 4 strategies: ballet, 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 boxing, 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 and boxing ballet. So the husband really has 4 strategies now. So let us look at the payoffs now. So wife playing ballet and husband playing ballet. So that's going to be this and this. So obviously the game ends up here, right? So the payoffs are going to be 2, 1. Let me copy this diagram itself here. That would be easy. So let me write it. Wife playing ballet or boxing, then the husband choosing ballet, boxing, ballet, boxing. So both choosing ballet means 2, 1, 0, 0, 0, 0, 1, 2. Okay. Now the second strategy is the wife playing ballet, husband choosing ballet here and boxing here. So obviously the game ends up here. So again the payoff is 2, 1. Now in similar manner I can proceed in boxing. The wife plays boxing, the husband plays boxing here and boxing here. So the game ends up here. So the payoff is going to be 1, 2. And no, sorry. Wife is still playing ballet. No. Wife continues to play ballet, right? So the payoffs are going to be 0, 0. And the final cell, wife plays ballet, husband plays boxing here and ballet here. So the payoffs are still going to be 0, 0. Similarly, when the wife plays boxing, so I'm going to fix wife's strategy as boxing. Then looking at husband, ballet. So this is going to be the payoff 0, 0. Ballet boxing. So in ballet boxing, what he does here is ballet boxing, right? So ballet and boxing. Ballet here, boxing here. So this is going to be again 1, 2. Okay, boxing is again 1, 2, and boxing ballet. So he picks boxing here and ballet here. So that is going to be 0, 0.
So in the first row, the wife is playing ballet, and in the second column, the husband is playing boxing.
No.
So won't it be 0, 0?
So which one? First row, second
First
column.
row, second column. Yeah.
Okay, so in this one, the wife is playing ballet. Okay, so the wife is playing ballet, and the husband is playing ballet in the first decision mode and boxing in the second decision mode. So the game ends actually here. Okay, so the first number, the first figure here represents what the husband does in decision mode 1. This is decision mode 1. And the second number represents what he does in decision mode 2. So this is decision mode 2.
Okay.
Okay. So this is how we treat sequential games. This is how we are going to write the matrix format of the sequential games. We are going to write all these strategies. Okay, so this is how we do it. Now, tell me what are the Nash equilibria of this matrix using the standard star mark technique. Tell me the Nash equilibria. Okay, so I'm just going to mark the cells as cell 1, 2, 3, 4, 5, 6, 7, and 8. So you can just tell me which cell numbers are Nash equilibrium.
So 1, 2, and 7.
1, 2, and 7.
So you're saying 1, 2, and 7 are all Nash equilibria. Yeah, I'll wait for others.
Yes, sir. 1, 2, and 7.
Does anyone need more time? Okay. Okay, Madhur, I don't want it in 1, 2, and 2, 1 format because then it becomes confusing. What are you telling? Which 1, 2, and which 2, 1. So that's why I clearly gave numbers to these cells. All right. So yeah. So which are Nash equilibria? If I pick strategy as ballet, then this one gives, then this strategy gives 1, this strategy gives 1, this is 0 and 0. So I'm going to circle these. And when I fix this as boxing, then this strategy gives 0, this gives 2, this gives 2, this gives 0. So I'm going to circle them. Now, when I fix up this strategy here, then 2 is greater than 0. When I fix this strategy for the column player, then the row player is better off playing this one. When I fix this strategy, then the row player is better off playing this one. And when I fix this strategy, the row player can play either one. So I'm going to circle both of them. Okay, not circling none of them, circling both of them. So that's how we do it. Okay, so obviously the cells in which all of them are circled, all numbers are circled, are these 3 cells. Okay, so there are 3 Nash equilibria now. So Nash equilibrium number 1 is ballet for wife and ballet for husband. Nash equilibrium number 2 is ballet for wife and ballet, boxing for husband. And Nash equilibrium number 3 is boxing for wife and boxing, boxing for. So there are 3 Nash equilibria. So there are 3 Nash equilibria. Now I want to introduce the concept of subgame perfect Nash. Okay, so this is something which they have been asking a lot in recent years. Subgame perfect Nash. Okay, so what is subgame perfect? So first of all, I have to understand what are subgames. So the game that follows any decision node, the game following any decision node is a subgame. Take any decision node. So this is a subgame. This is a sub-game. This entire thing is a sub-game. So there are 3 sub-games. Number of sub-games is equals to number of decisions, because everything following a decision node is sub-game, right? So now the question is, what is sub-game perfect hash? So the idea is, look at this strategy profile, ballet, ballet, ballet. So the game looks like this, ballet, ballet, ballet. Now the game proceeds in this direction as soon as the wife picks ballet. So what's happening in this decision node is ideally immaterial. But this is what subgame perfect Nash tells me, that even the subgames, which are the decision nodes which actually don't get reached, your strategy should not be something which is illogical at such decision nodes. Okay, so suppose the husband has outsourced the decision making to his secretary. Okay, so the wife gets free from office first. She picks whether to go for the ballet or the uh, ballet performance or the boxing match. So step 1 is at 4:30 p.m. wife chooses ballet or boxing. Okay. Step 2 is husband is in a meeting till 5 p.m. So he tells the secretary to book a cab for him. So the husband is in a meeting, he tells the secretary, book me a cab. But a cab to where? So this is where these 4 strategies come into the picture. In strategy 1, what you're basically telling to the secretary is, book me a cab to the ballet performance, irrespective of what the wife does. In strategy 2, you're saying, book me a cab to the ballet performance if my wife goes to ballet performance. Book me a cab to the boxing match if my wife is going to the boxing match. So in strategy 2, you're telling the secretary, you'll get a call from my wife where she is gone to, and you book me a cab to that location. In the third one, you are telling the secretary, I want to go to the boxing match irrespective of what happens. Okay. And in the 4th strategy, you're telling your secretary, I want to go to boxing if my wife goes to ballet, and I want to go to ballet if my wife goes to boxing. So I just don't want to see my wife. So this is what these 4 strategies are using. These are the set of instructions that you can tell to your secretary to follow, depending on what you want to do. Okay. So now what happens is that even though the wife is picking ballet, what happens here is immaterial. It will become materialistic if, suppose, not materialistic, it will become important if suppose for some reason the ballet performance is cancelled at the last minute. So suppose in a situation like this, the wife always is the first mover and you're the second mover. But if for some reason the ballet performance is cancelled and you move to this decision node, then your secretary should know that what to do in this decision node. And that is subgame perfect match. Okay. So let us try to see which of these 3 strategies are subgame perfect. So ideally, what should I do when I reach if this decision node is reached? So if this decision node is reached, then by picking ballet, the husband gets a payoff of 0. By picking boxing, the husband gets a payoff of 2. So he should pick boxing and decision node 2. Right. So in decision node 2, he should be picking boxing. right? So in decision node 2, he should be picking boxing. So that's why this is ruled out. This is not subgame perfect, because in subgame perfect, in this strategy profile, you're saying that if this decision node is reached, send me to the ballet performance. That is in logic. Similarly, what should the husband do on this decision?
So ballet.
Ballet.
Ballet, right? Because ballet gives a payoff of 1, boxing gives a payoff of 0. So in decision node 1, he should pick ballet, not boxing. Irrespective of whether this decision node is reached or not, if it is reached at this decision node, you should always pick ballet. So this is ruled out. So the only Nash equilibrium which is subgame perfect is this one. This is the subgame perfect Nash. Which incidentally is also the backward induction result. Now, what is backward induction? I'll come to that, but first I want to delve into subgame perfect, because I treat it as a very important question, very important topic, because of late they have started asking a lot of questions from backward induction. So let me just pick a question from past year. Okay, let's take this question from DAC 2018. I've not added 19 and 20 problems, but they have asked subgame perfect in both these years as well. You can find those papers in the, I'll add them, I'll add all the papers in the study material section. In any case, let's look at this question. Player 1 moves first and chooses left or right. If she chooses right, the game ends and the payoffs are 10 or 20. So player 1 chooses right or left. If she chooses right, the game ends, payoff are 10, comma. So this is player 1. If she chooses left, then player 2 moves and chooses either left or right. So then 2 chooses from left or right. If she chooses right, the game ends, our payoff are 0, comma 20. If he plays left, then player 1 moves and chooses left or right. So again, player 1 moves, chooses left or right. The game ends in both cases now. If he chooses left, payoffs are 30-30. And if he chooses right, the payoffs are 40, commas. So I have to find the Nash equilibrium of this game. So let me copy this thing. Okay, so this is my game. Player 1 has 2 decision nodes. Player 1 has 2 decisions, whereas player 2 has a single decision. So player 1's strategies are left, 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 right, right, left, right, right, right. So he can choose either strategies in either decision nodes. So this is my player 1. Player 2 has only 2 decision node, 1 decision node. So the strategies are going to be left and right. So why don't you guys now fill this table and tell me, fill this table with the numbers and tell me the Nash equilibrium. Okay, so I just give you cell numbers 1, 2, 3, 4, 5, 6, 7, 8. Fill the table. You have the entire game here. Fill the table. Give me the Nash equilibrium. Not subgame perfect right now, just the Nash equilibrium. Yes. Anybody? Let me start filling the table. So when player one plays right in the first instant, the first decision node being right, then everything immaterial payoff is just going to be 10, 0. When he plays left and the other guy plays right, so left followed by right, the payoffs are going to be 0, 20. So left followed by right, so 20. Now left, left, left is the straight pathway, so that's going to be 30, 30. And left, 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 right. That's going to be this path, left, left, right. So that's going to be 46. Did everybody get this right at least? Do we have any doubts here in this step? Okay. Now, second step, just tell me the Nash equilibrium of this matrix using that circle technique or star mark technique, whatever you want to call it. The best responses, using best responses. You're getting all of them as Nash equilibria. Okay.
So 5, 6, 7, 8.
All of them. Right.
So I'm getting 6 and 8.
6 and 8. Okay. Focus. I mean, this part should not be wrong. This is the most important part. You don't get any marks for doing this right. It's like differentiation. Okay, you have to get it right, but just doing it right will not give you marks. There are further steps involved in solving this problem. This is the
Sir,
first step.
6 and 8.
6 and 8. Okay, so some of you are saying 5, 6, 7, 8. Some of you are saying 6 and 8. So let us see. So when I fix this strategy, the best thing for player 1 is 40. And when I fix this strategy, the best things for player 1 are 10. Now, when I fix this strategy, the best thing is 30. When I fix this, the best thing is 20. When I fix this, they are both good, equally good. When I fix this, they are both equally good. So the only strategies in which all the numbers get marked are these 6 and 8. So these are my Nash equilibrium, 6 and 8. Just let me leave them. So these are my Nash equilibrium, 6 and 8. Okay, so you should not be getting this wrong. I cannot stress this enough. Focus, and when you're doing it, it's not that difficult actually. Just you need to be more attentive. So make sure you don't make the mistakes of looking at the wrong numbers. I still do it. I hope you won't. Anyway, after you do the first problem set, you'll get much more trained in this. But remember, this part is tricky. It gets tricky, and people are bound to make mistakes. So be more attentive when you're doing this. Now these are two Nash equilibria. Right. So now that I have Nash equilibria, I want to analyze which of them is subcable. So one strategy is RRR. The other strategy is RLR. So the only difference is in the third decision node 3. The only difference is what's happening here. Everything else is same in these strategies. So let me just analyze this decision node. So this here, the decision is being made by player 1. So what should player 1 do here ideally? Should he go left or should he go right? What should he do?
So right.
Right, because right gives him higher payoff. So he should be picking right. So this is my subgame perfect Nash. So he should pick right. So what's happening here is that in this strategy, RRR, this is what's happening. The actual payoff is 10, 0. So player 1 picks right in the first instance itself. Correct? Now, notice that this strategy profile, LLL, takes them to 30, 30. Both of them are better off. But the actual thing which happens here is 10, 10, which is not a good deal for either of them. But why is this thing happening? Why is 10, 10 still happening? Why is this an equilibrium? Can you give an answer from a societal perspective, maybe some psychological perspective? Why in this game am I getting 10, 10 as an equilibrium? When there's a clear-cut better option, both these players could be at 30, 30. So why is that not happening here?
Because if by any chance the first player takes an L, then second has an option to take R, which will give him better payoff. Then
Yeah, exactly. So the idea is, in order to reach this 30 commodity, so what you're saying is basically true. It's mistrust of the other guy. You don't trust the other guy. So for to reach here, you have to reach this decision node. Now at this decision node, player 2 cannot trust player 1. What if player 1 plays right? He gets a 40 payoff instead of 30. So you cannot trust player 1 to play left when he reaches this decision node. So that's why as soon as player 2 gets the opportunity, because he cannot trust player 1, he will play right. Because he does not know if the game goes here, it will actually end up here. It may as well go downwards. And when it goes, player 2 ends up with 0. So better to stick here at 20. So because of this, player 1 now cannot trust player 2. So neither of the players can trust each other. So when this option of 30, 30 is clearly available, even then the players actually end up at 10, commas. So this is Nash equilibrium. This is the nature of Nash. It's not. This is a very good example to teach you that Nash equilibrium is not payoff maximizing equilibrium. It is nothing other than no incentive to deviate, because at this point, no player has an incentive to deviate. From these green strategies, no player at any sub game on any decision node has any incentive to deviate. Okay. All right. So that wraps up this one. What will be the correct answer here? Has a unique Nash equilibrium. Okay. These options I have typed wrong. Has a unique subgame perfect Nash equilibrium. That was one of the options. So that would be the correct. Has a unique subgame perfect Nash. Okay. So the actual pair subgame perfect is RRR. So there is no subgame perfect equilibrium in which 2 plays L. So the unique subgame perfect Nash equilibrium outcome is RRR. Okay, so there's a unique subgame perfect Nash. All right, I wanted to talk about backward induction, but we are out of time, so I'll stop it here. Let me see the problem sets. Yeah, you can do these problems. You can start doing these problems. I think we have done most of them. You can leave mixed strategies. Most of these are mixed strategy cases. So you can leave wherever you see mixed strategies because it's not in the syllabus. So that will eliminate like 60% of the paper. I think only true false will be left. But that's the issue here, that the problems, they involve a lot of mixed strategies, but since it's not in the syllabus, there's no point doing that. All right. So